Hello everyone, and welcome back again. So this time we're going to be going over the rectangular components of our position, velocity, and acceleration. And I will be honest with you, this gets very repetitive very quickly because we're going to be going over this for the velocity, position, and acceleration, and it's very similar. Said very way too much. So the position of a particle at any time can be defined by our position vector. And we can break that up into its x, y, and z components. Where x, y, and z are the magnitude, and the I, j, and k right here are the vectors. They give the direction. I along the x-axis, j along the y, and k along the z-axis. These are all unit vectors, which means their magnitudes are 1. And x, y, z components can also be functions of time, which if they're functions of time, that means we can actually differentiate them. The magnitude of the position vector, so the distance from the origin to your particular point, is going to be r, which is simply kind of like Pythagorean theorem here, but for 3 dimensions. X squared plus y squared plus z squared. So each of our components squared, and then we take that square root of that. And the direction of our r is defined by the unit vector, which we can use this notation, and it is simply our position vector divided by the magnitude of the position vector, which we calculated just a moment ago. A lot of times you'll see me write this as this in problems, where no hat means it's a scalar, and the hat right here makes it a vector. And we can actually do the exact same thing with our velocity vector, because our velocity vector has both x, y, and z components, and since x, y, and z can change with time, we can differentiate them. And what we do is we just change it to Vx, Vy, and Vz. Those are velocities in those particular directions. We can also term this as x dot, y dot, and z dot, where the dot says that that's a time derivative. So there's 2 dots, it would be d squared z dt. So 1 dot is just the regular d dt, a single derivative. And as with previous, we can take the magnitude, which is the speed, by taking our components, squaring them, and then taking the square root of the sum. The direction of v is always tangent to the path of motion. Always tangent to the path of motion. Then finally, acceleration. Once again, we just take a time derivative, but this time of our velocity, which is also the second time derivative of the position vector. And if we want to, we could call this ax, ay, or az. Or we can say this is Vx dot or x double dot. This is usually very helpful to think about it this way, especially when they tell you that velocity is constant. Well, then the velocity in the x direction maybe is constant. Well, then that would be 0. Or if the position vector in the x direction is 0 and constant, well, then that would be 0. We have lots of different things we can use here to help ourselves out and simplify our equations. And as left the last few, we can take the magnitude of the acceleration vector, and the direction of A is usually not tangent to the path of the particle. If it's a straight line, yes, it will be tangent because it's going in a straight line. Other than that, it doesn't usually happen. It follows the hodograph of the velocity, which is just where is the velocity, the end point of the velocity every single moment, because that is what the acceleration is changing. Okay. So hopefully you've mastered this by now, because we have this same equation over and over again. We square the components, we add them together, we take the square root. That's how we get our magnitude. And if we want to find directions, well, we just take our vector right here. If we get that unit vector, then we divide it by its magnitude. Little arrow or hat, vector, no arrow or hat, not a vector. So I take the vector and I divide it by the scalar. And what this does is it gets rid of the magnitude, so it makes it just magnitude of 1, and it's pointing in the correct direction. That can be very helpful for us, especially if we're trying to figure out what a force is. If we're trying to figure out the direction of force is being applied based on our acceleration, what's going to be along that same unit vector. Okay, so we've worked hard, we've done this, but now we actually need to try out some problems. So next time, we're going to jump into an example problem. I hope this helps you, and I'll see you all next time.